Hi. Today we're going to talk about the next topic, which is momentum. And in this case, it's a linear momentum to distinguish it from angular momentum, which we'll talk about later on. And momentum is really the culmination of a topic that we started to talk about way back in Unit 2, which is inertia. So even then, you were thinking about the fact that inertia is a resistance to a change in velocity. And so it's part of the reason why you can't stop a train, let's say, by parking your car in front of it, right? So the car with its low mass will not win the fight against the train with its very high mass. So the mass part of it we talked about in the past, I think makes sense to most people. Where things get a little bit confused, though, is if I were to, let's say, take a ball bearing. Okay, so here's me, right? You can tell it's me. So handsome. There you go. And I have a ball bearing, and I take that ball bearing and I throw it over to you. There you are. Nice. Okay, throw it over to you like so. My guess is that you'll probably easily be able to catch it. Okay? No problems, right? On the other hand, if I develop a device which is a sort of a gun that shoots out that ball bearing at a very high rate of speed, so much so that it doesn't even bend as it gets to you, it's going so fast, it's going to be much harder to catch. And so as a result, you can see if you had to choose one of the two to be launched at you, you probably would choose me just throwing it gently to you. Did the mass of the steel ball bearing change at all? No, the mass was the same. And so each time it had the exact same resistance to a change in motion, or resistance to a change in velocity. So when you're catching it, were trying to change its velocity. But each time it had exactly the same resistance. So why is one harder to catch than the other one? And the answer is that inertia is not the whole picture. Okay, so inertia explains things like this a little bit, and it explains other things, but it doesn't explain this, where you're talking about two objects that are exactly the same in every single way, and yet one object is almost every single way, and then one object is harder to change the motion for than the other one. And so we have our next formula here, and I've written it right there. Boy, that was a terrible, terrible box. Sorry about that. I will erase it. And it says the momentum of an object is equal to its mass times its velocity. So I'm going to go ahead and write this down. It's momentum. Momentum's kind of tricky because it's a word that we use oftentimes in things like sports, right? You feel like you have momentum if things are all going your way. And that kind of has a relationship to what we're talking about here. But we obviously, as always in physics, need to be more specific about what we're talking about here. So momentum is this number, it's this quantity that takes into account both the inertia, right? So this is mass, but we know it's actually measuring inertia, and motion, which we know here is velocity, right? And so both of those things are important, as you saw with the ball bearing tossed to you and shot at you. And so we're going to need to discuss that idea, this concept of momentum, anytime that things collide. So, for example, I picked up an image of Clay Matthews sacking Drew Brees here, not just because it's fun to watch and all that, but because it illustrates momentum, right? And so Drew Brees initially, I'm going to draw him out. The stick figure here is Drew Brees. He's got the ball, right? He's ready. I'm going to draw his little football helmet. Oops. Boy, my pen doesn't like it when I try to draw things too small there. There we go. That'll be good enough for us for right now. There we go. There's his football helmet. So he's getting ready, and of course, Clay Matthews is starting to dive at him, right? Now, Clay Matthews is probably sprinting his way over towards Drew Brees. And so if you look at it here, Drew Brees is standing still. Clay Matthews is flying at him. He's running as fast as he can at him. Now, here I actually looked it up. Clay Matthews has a mass of 116 kilograms. Drew Brees has a mass of 95 kilograms. So we're pretty sure that Drew Brees is going to be easier to change the motion of than Clay Matthews right here. And I don't think that should come as any surprise. Anytime you're going to be on the defense, you're definitely going to be a little bit more massive than the quarterback, right? That's part of the reason why they beef up, right? So the other part of it, though, is that we have to take into account their motion. And so Drew Brees here has a momentum that looks like this. The mass times the velocity, right? We know that. And so his momentum is 95 times 0. So what is his momentum? It's 0. And the units for momentum are, because it's a mass times velocity, are kilogram meters per second, which I know is weird, but it is the way that it is. On the other hand, look at Clay Matthews here. Clay Matthews on this side has a momentum that's equal to also his mass times his velocity. And so let's take a look at what that looks like. It's 116 times his velocity, and well, let's just give him a velocity of, I don't know, 10, just because it's the math is easy, 10 meters per second. Okay, and so what's his momentum? 1,160, and I'm not worried about sig figs here, kilogram meters per second. Okay, so you can see who has the momentum, and when they collide, we're going to have to take both of those momenta into account. So that's going to be our next task as we go through this, as we start to talk more about collisions. Don't forget that the momentum is actually a vector, and so we have to make sure that we draw it out like a vector, like so, right? There we go. So it's a momentum vector, and we know it's going in the direction that his velocity is, right? The direction that he's moving. Same thing with this train. As it was moving, it had a velocity coming this way, and so therefore its momentum was also going in exactly the same direction. So now we're set up to talk about, mathematically, to talk about how collisions work. Hope you enjoyed it. Let me know if you have any questions.